Welcome. In this particular lecture, we are going to analyze the output impedance in digital current mode control with and without load current feed forward. So, here output impedance analysis under current mode control we will discuss, and then what will happen with the output impedance if the load current feed forward is added, and what is the output impedance with and without load current feed forward, that we are going to consider with load current feed forward, how it is going to alter the output impedance. We know about this mixed signal current mode control, we have discussed multiple times, but here we have considered the load current feed forward inside the digital platform, and it is like an estimated load current, because actual load current we are not sensing, and we are assuming this converter is driving a processor or it can be LED load, and for LED load anyway the load current information can be indirectly obtained, because we know the nominal string current and we are turning on and off multiple strings. So, we can estimate the load current pretty accurately, but in case of processor if we communicate, then we can get the information of the load current. So, if we incorporate load current, then first of all the current mode control we have considered that delay can be added, because we want to talk about the small signal design of current mode control, and this small signal model of traditional continuous time current mode control and the digital current mode control will be more or less same, mixed signal current mode control by incorporating this delay. But since the delay is very small, it has insignificant effect. I would say you can treat e to the power minus s tau d almost approximately equal to 1, because it has negligible effect. Okay. But we want to analyze what will happen with and without load current feed forward. So, this is the loop transfer function, and what will be the output impedance? Now, in our condition, on our case we are taking this 1 by Kc, because we have a current sensor gain, and that we have discussed, because here actual inductor current we are not sensing, and there is a current sense amplifier, current sense resistance followed by current sense amplifier, and this is 0.01 volt per ampere. Okay. Next we have a feedback voltage gain, which is like a 0.27, and we are dropping some bit. So, it is resulting into a gain of 1 by 4, and this is clubbed together. So, now your loop transfer function will look like this, and here we will also have e to the power minus s tau d, but you can drop this term, because this is almost 1, because the delay is negligibly small compared to the time period, and this is the overall loop transfer function. We have discussed in our lecture number 38 in NPTEL course without delay, that means what is the output impedance of current mode control, like for continuous time current mode control or analog current mode control. Now, the closed loop output impedance will be open loop output impedance divided by 1 plus loop transfer function. This thing we already know, and for a typical buck converter we know the output impedance is a function of ESR. Here it is the ESL inductor, that time constant, and then it has a pole. This thing we know, and we have discussed in our earlier course. Now, if we incorporate load current feed forward, so this is a load current feed forward, and this is a normalized gain, and this normalized gain, this gain equal to 1 for buck converter. For boost converter it will be V 0 by V ref for boost, for normalization, because we want to normalize this with respect to the inductor current. But here we are giving this, and then as if there is a DAC gain, then there is a current sensor. So, you have to scale this reference. So, what we are doing, although we are showing for analysis purpose, but actual implementation we are using like a I 0 estimate, and the value we are setting according to this scaling factor. So, that average inductor current, that scaling inside the digital platform should be consistent with the load scaling. Now, if we analyze with the load feed forward V 0, so if we write those step 1 by 1, this is for buck and boost, then V 0 if we write, then what are we going to get if you further write this expression in terms of. So, this is our total loop transfer function. So, loop transfer function is a product of this term, all this term product including this. So, all this product will give you a loop transfer function. So, V 0 can be written by like this, and if we write output impedance, so it will look like this. Now, since we have taken this term to be approximately equal to 1, and we know from our earlier course that control to current, because if you take the inductor current, whether it is a buck or boost. So, this is our inductor current, and if you take the small signal inductor current, that means I L tilde, we have considered in current mode control, this can be replaced by a control current source in the small signal sense, and this will be inductor. So, that means if we take I L per term by I C per term, so this will be, this transfer function is nothing but our G I C, but this will be approximately 1 with the first order transfer function, that means which is a very rudimentary model we saw, and that was good enough to design current mode control without ramp compensation. And if you make that, then this GIC will be 1, and this will can be scaled to make it 1, and if you do that, because the whole loop gain, then it can be shown that 1 minus GIC this into Z0 divided by 1 plus loop transfer function is my output impedance closed loop with load current feed forward. Of course, there is a Kn turn is there, Kn term is there. So, if Kn equal to 0, then it is simply Z0 by 1 plus loop, that means there is no load feed forward. If this equal to 0, then there is no load feed forward, then this will be the transfer function. But if Kn equal to 1, and since this can be approximately equal to 0, because this guy is approximately equal to 1. So, which means your closed loop output impedance will become nearly 0 with load current feed forward, and we will be taking experimental case studies show that will have insignificant impact on the undershoot and overshoot of the output voltage when there is a load step transient, because this will make the output impedance almost 0. So, it will take somewhat closer to an ideal voltage source. So, in summary, we have discussed output impedance analysis under current mode control, and we have also considered load current feed forward and their mixed signal implementation aspect, and we have analyzed the output impedance under current mode control with load current feed forward. So, in the subsequent lecture, we are going to consider experimental case study using with and without output load current feed forward and show what is the impact on the load transient performance. That is it for today. Thank you very much.